This video is on Charles, Boyles, and Gay-Lussac's law. So in all the different gas laws that we're going to look at, they all involve, in one way or another, pressure, volume, temperature, and moles. And we're going to look at the different mathematical relationships between these four variables. Sometimes they will be directly proportional, meaning as one goes up, the other will go up. And sometimes they will be inversely proportional, which means as one goes up, the other will go down. As you can see here, Boyle's law has to do with pressure and volume. And it says that they are inversely proportional. So again, that means that as you apply pressure to something, the volume will decrease. You can think of a syringe when you're thinking of this as when you're pressing the syringe down, the volume inside the syringe is decreasing. Charles' law talks about volume and temperature, and it says that they are directly proportional. This means that as the temperature goes up, the volume will go up. You can think of a hot air balloon as your example for this. That as you increase the flame in the hot air balloon, as you increase the temperature, the balloon expands and gets bigger, and that is Charles' law. And the third law here, Gay-Lussac's law, talks about pressure and temperature being directly proportional, similar to Charles' law being directly proportional. With pressure and temperature, you can think of any aerosol can. That as the temperature, if the temperature increased in that can, the pressure would be increasing too, and that would lead to it blowing up. Important here is that your temperature has to be in Kelvin. And that is the same thing for Charles' law. Anytime you are given temperature, you must convert it to Kelvin. And as a refresher, to do that, you take your Celsius and add 273.15. So Boyle's law, here is the formula you need to know. And that is P1V1 equals P2V2. P stands for pressure and V stand for volume. The ones and the twos stand for initial and final. So sometime you will see this formula written for P initial, volume initial equals P final, volume final, or the ones and twos mean the same thing. It does not matter. What we're doing with these formulas, we will be given 3 of the 4 variables. Notice we have 4 unknowns here. So we'll be given 3, and we're just going to plug them in and solve for the 4th one using algebra. So the first example here says a helium balloon with a volume of 1.1 liters and a pressure of 0.91 atmospheres expands to 3.1 liters after being taken into the mountains. What is the new pressure, assuming no change in temperature and no gas has escaped? So I like seeing what we have right now. So it says we have a volume of 1.1, so that is a V1. I see I have a pressure here of 0.91, that is a P1. And it says it expands to this volume, that is my V2, and it's asking for the new pressure. So that's P2. So we know this is Boyle's law because it's the notes and it's right after the slide. But when all these laws are mixed, you want to label everything and see, okay, I have 2 P's and 2 V's. That means I'm using Boyle's law. So I'm just going to rewrite the law here. And now I'm just going to plug stuff in. So my P1 is 0.91 ATM. My V1 is 1.1 liters. My P2 is like my X in my algebra equation. I don't know what that is. And my V2 is 3.1 liters. And now just with math, I'm going to multiply the left side together, get those, and what I'll do is I'll end up dividing both sides by 3.1 liters. And you can do this ahead of time. Do it as one big step. That'll work too. Just watch your significant figures. The other thing you want to make sure of is that your units are the same. So like volume here, we have liter. So we're left with atmospheres. So that's just something else. If you had different units, you would have to convert them to make sure that they're the same. So when I do this in my calculator, I get 0.32 ATM. Here you can see the human body with the lungs expanding and contracting. So when the air is inhaled here, coming through here, your lungs are getting bigger. And then when you're exhaling here, they're contracting. The pressure gauge on a patient's full 10.7 liter oxygen cylinder reads 8.5 ATMs. At constant temperature, how many liters of oxygen can the patient's tank deliver at a pressure of 0.92 ATM? So again, I'm just going to go through and start labeling stuff. So this is my V1, and I know that because my unit liters. 8.5 ATM is my P1. The question's asking how many liters, so that is my V2. I don't know that. And then this is my P2. So it looks like I'm using Boyles' law again. So I'm going to rewrite my equation and start plugging stuff in. Notice my pressure is in ATM both times, so I don't have to worry about converting anything there. And I'm just dividing both sides by 0.92. And my V2 equals 84 liters. Another check you can have here, we know that Boyle's law is inversely proportional. So look what's happening to the pressure. The pressure is going from 8.5 to 0.92. So the pressure is going down, which means the volume should go up. And look what happened with the volume. We started with 10.7 and we ended with 84. And you can always check that in these problems. If we go back to the other one, look what happened to the volume. The volume went up, so the pressure should go down, and it went from 0.91 to 0.32. So that's a nice check that we have. The next law is called Charles' law. Here is your formula for Charles' law. So we have two fractions here, looks like a proportion. We have V1 over T1 equals V2 over T2. The 1s and the 2s mean the same thing for final and initial. The V's are your volume still, and your T's are your temperatures. So again, we want to be very careful here that our temperature is in Kelvin. That is key. We're really going to set this problem up the same way. We're going to label what we have and then go from there. So it says a 19.5 liter sample of neon, right there is my volume, is cooled from 76 to 38 degrees Celsius. So 76 would be my T1. And I know I need to change that to Kelvin. I would do that right away so you do not forget. 349 Kelvin. And my T2 is 38 degrees Celsius. And that's 311 Kelvin. What is the volume? So it's asking for my V2. So I know I'm working with Charles' law. And then you're going to plug stuff in carefully. Now algebraically here, with Boyle's law, we divided both sides by a number. Here we are going to multiply both sides by 311. And when we do that, our V2 will be 17.4 liters. The nice check that we have here, Charles' law, volume and temperature are directly proportional. So what happens to one happens to the other. Our temperature went down. Our volume should also go down, which it did. Gay-Lussacs law. Your formula for Gay-Lussacs law is P1 over T1 equals P2 over T2. P stands for pressure here. Everything else is the same. Remember to put your temperature in Kelvin. This is treated exactly the same as Charles' law, algebraically. The only difference is you have pressure instead of volume. Before leaving, your tire pressure is 35.2 psi. That is my P1. The temperature is 25 degrees Celsius. So I'm going to change that right away. And I get 298 Kelvin. I have to watch my significant figures here. I should have one decimal point to the right since I'm adding. So 298 point, that would be 2. 298.15, so 298.2, yep. After driving, the tire pressure is 36.5 psi, so that is my P2. What is the new temperature? So T1. We are looking for T2. And again, we're going to be multiplying both sides by the denominator. And our T2 equals 309.16 Kelvin, or 36 degrees Celsius. So that is Gay-Lussacs law.